Alright guys, with this, here we go. With this video, we're going to talk about 4.8, which is Newton's method. And when I say Newton's method, it's Newton's method to finding zeros, roots. Now, all your whole math life, you've been talked about, like told, you need to find the solutions, you need to find the zeros, you need to find the roots. So much so, we have so many different ways to solve it. We say solve an equation, find what x equals, solve for x. That's usually, we set y equal to 0, solve for x. That tells us where the intersection line is of the y-x axis. You have the quadratic formula that we've learned and we've known for so long to find zeros. We have just factoring to determine, using the zero product property, like when is the x-axis going to be equal to 0. And so because we have all these different solutions to find zeros, that's helpful if those things work. But the quadratic formula only works for like quadratics, and not everything can factor, and not everything has a beautiful root. Not everything is going to be like nice and neat in the real world. And so what we have then, if like these analytical methods don't work, we have ways that we can like kind of brute force it or come up with really good approximations to what that root is going to be. Okay, so in order to teach you what Newton's method is, here's what we're going to do. We're going to have a graph here. And we're going to say this graph looks something like this right here. Now I'm going to call this one right here. Nope, we're going to do it with this one. That's going to be r. That's going to be my root. So I know that at r, y equals 0. Okay? So what we're going to do is we're going to pick any point here. That's kind of in this area. And we're going to say, okay, I'm going to pick this point. And we're going to call it x. Then I'm going to find the slope of the I'm going to find the tangent line at that point to the graph right there. And then this point right here becomes, can I zoom in? No, but I can draw it bigger. So we have down here, remember at this point right here we have, it's going to be coming down and up like this. So that slope of the tangent line looks kind of like this. This point right here is we're going to call x1. This point is x. This is r. Then what we're going to do is we're going to take x1, we're going to come up here, and we're going to draw another slope of that tangent line right there, which this point we're going to call x2. And if you notice, eventually, as we take slopes of the tangent lines all the way as x approaches, as we do this, our x's are going to approach r. Let's give you some better pictures. So if I'm going to go to the textbook on this one, which I know I don't normally do, but we have these three pictures, which I think I can zoom in on this one. Maybe I can't. Well, let's look at it. So what we have is we have this line right here, and we have the slope of the tangent line. So our initial point is x0, slope of the tangent line at that point right there. And then we have x1, it goes straight up to the new point. x0 is over here still. And we draw the slope of the tangent line at that point, and we get x2. And then we're going to draw the slope of the tangent line at x3. And then we're going to draw the slope of the tangent line at x4. And so all of these points are going to have slopes of the tangent lines that are like this. We have y minus RF of some x. We've done this so many times, right? F of x sub n, which is going to equal our slope of our tangent line, f prime of x sub n, times x minus x sub n. Okay, so what this is saying is at some point x, I keep doing this and keep doing this and keep doing this, I'm going to be able to determine what this r value is. But if you notice that the r value, my y is 0. So I'm going to say, well, this is going to be 0. And what I really want to do is I want to find this one, because that's going to be my next point that I'm looking for, right? So I'm looking for the next x value is what I want to do. So if I solve for this, I'm going to get x equals f of x sub n divided by f prime of x sub n times x sub n. Now, when I say this like this right here, this x sub n, I'm going to factor it out and we're going to be okay. So what that's going to do for us is this tells us in order to find the next one, the next x value we solved for x, we're going to get this x. Oh, I see what I did. I'm sorry. I got to distribute this first. So let's ignore all of this. I erased more than I wanted to. Okay, so this is going to be negative f of x sub n equals f prime of x sub n. So then I'm going to divide that over right there. So I get f negative f of x sub n over f prime of x sub n equals x minus x sub n. So I add x sub n over and you get the next one, or x, we're going to call that n plus 1, equals x sub n minus f of x sub n over f prime of x sub n. And this is how I get my next value based on all my previous values. Okay, so that's what this is saying right here. So it says end the calculations when the termination condition is met. So let's say we're trying to find the solution method and we get something like x sub 7 is going to be 4.835789. Yes, these are going to be like really, really hard roots, because if they were easy roots, we could do our other methods to solving this. So Newton's method is going to help us find these harder roots. Let's say x sub 8 is equal to 4.835590. So you see it's a little bit different. Then we do x sub 9, because like where are we at? 4.83590. So as soon as I get 2 in a row that are like it, that's a really good approximation to this decimal point. This is correct up to this decimal point. So if it says, hey, you need to have 6 decimal places correct, you keep doing it until 6 decimal places repeat twice. And the beautiful thing about this method is because how it's designed with the slope of the tangent line, it's going to approach that root speedily. Doing it 9 times might be a little much on some of these, unless it asks for like 10 decimal places, which if it does, don't do that problem. Email me and I'll say, don't do 10 decimal places. That's insane. So what you're going to do is you're going to be given a function that doesn't have good roots. Something like x to the 5th plus 14x cubed plus 8x squared plus 4x plus 3. And trying to graph that and find out where it is actually going to be equal to 0 is going to be hard. But what I do know is, hey, that's differentiable. And usually they'll give you like, hey, look, we're going to say let x sub 0 be 3. So the very first thing we're going to do is say, okay, well, to find x sub 1, I plug in x naught, which is 3. But I'll just write it out first. X naught minus my f of x sub n. So this is going to be 3 to the 5th minus 14 or plus 14 times 3 to the 3rd plus 8 times 3 squared plus 4 times 3 plus 3 divided by my derivative of this, if this is f of x. My derivative is going to be 5x to the 4th plus, that's going to be 42x squared plus 16x plus 4. So I get 5 times 3 to the 4th plus 42 times 3 squared plus 16 times 3 plus 4. This, well, I'm going to plug 3 in for this one too. So if I do that, you can see, hey, this is going to be my next step in my approximation. I do this about 7 times. Okay, whatever number gets here becomes my x sub 1. So then I do it, x sub 2 is going to equal x sub 1 minus f of x sub 1 over f prime of x sub 1. And then I do it again. X sub 3 is going to equal x sub 2 minus f of x sub 2, whatever we got there, over f of f prime of x sub 2. That'll give me x3. And then I'm going to keep doing this and keep doing this and keep doing this until I get this repeated numbers. Okay, 3.876549, and then if that was x sub 4 and x sub 5 equals 3.876549, which that's a totally made up number. Then, because it repeated, I'm going to be done. I'm going to say, yep, that's what I needed to do. Call it good. So the whole point of Newton's method is just try to find roots that work. Now, there is a pitfall to doing this. Okay, let's say you have a graph that looks like this. I don't know why, but I feel like my axes should be in black all the time. So we have a graph that looks like this. And it does something kind of like this. Kind of back up here. And I take the slope of this tangent line and I get right to there. Well, let's go a little bit more drastic here. I'm not being drastic enough, I'm sorry. We're going to say that the slope of this tangent line, I'll do it in blue, is going to be right here. I said blue and it came out as orange. Okay, this graph goes and touches it like this. And this graph actually is going to come up like this. So then I find the slope of this tangent line and it puts me right back here, which ends up being this tangent point again. And so I get the same two lines over and over and over again. My approximations become like cyclical, like I'm not getting closer to anything. So there's like that pitfall that's right there. And how you could do that if you start getting that is move this initial point over a little bit. And then all of a sudden you're not in that rut anymore, if that makes sense. So you'll start to see it. Now you're looking at this right here and you're like, well, yeah, you wrote a few things, but look at all the stuff you have to plug in. And the answer is yes, I know. It is a lot of calculations. So please use your computers, please use your calculators, please use your phones to help you calculate that. Make sure you're typing in things correctly. Take your time, because doing it and then getting wrong numbers is going to be frustrating because as soon as you get a wrong number up here, it's going to affect every single number down here that you have. All right, so good luck with Newton's method. There's not too many problems on your homework on this one, and I'm sure you're going to get the help that you need.